So in Chapter 5 of your Calc 1 course, you learned the definition of a Riemann sum, and you may not remember it, which is why I wanted to do the video. You're familiar with the definite integral, and this is how integration was introduced to you. It was a definite integral from a to b of the integral of f of x dx, and it's basically shorthand notation for an actual limit of a summation as our n value goes to infinity. So I want to talk about the right-hand side because at the end of this course, we're going to spend a significant amount of time talking about summations and what the integral sign means in general. So once you learn your definite integral, then we talked about the general integral, which is just the antiderivative of the function. But this is going to be specifically about definite integrals. So I have a graph of f of x here. It's just some function that's differentiable, and we'll say that it's between a and b. And I just want to go over the definition. So when you learn this, you learn that this represents the area under this curve that's bound by the curve and the x-axis, and that's still true. But my hope is by the end of Calc 2, when you see an integral, you don't just necessarily think about the summing up of areas of rectangles. I want you to think about it as the summing up of infinitely many things. So even in Chapter 6, we're going to see that happen. So the integral sign is actually going to represent the adding s. That's why it kind of looks like a s, sum, of infinitely many things. Now in this case, when we use it in this definition, it's going to be infinitely many rectangles. And so there was a few ways that you learned to do it, and you learned the right end point rule, the left one, and then the midpoint one. And I think Dr. Lee will go through those briefly, and then we'll learn about two other rules that you'll need to know about in section 5.9. So remember how we did it. We had our two endpoints, A and B, and you actually are going to break them up into equal intervals. So those intervals are our delta x, and that by definition is the difference between a and b, so that's just b minus a divided by n. That forces it to be a positive number. We want the difference to be positive. And n is the number of rectangles that you would use to separate your a and b. How many rectangles do you want? Now, remember, what we're really going to want is infinitely, but of course we're doing a example, so that's never going to happen. So you pick an n. So whatever that n is, you might do 5 rectangles, and you'll see Dr. Lee do some of those. But what you do is then you go down to your number line, the x's, and you label them. So a is going to be the same thing as x naught. That's how we say that, x naught. And then you'll have x1, where this difference here is the delta x value, whatever the value is, depending on the number of rectangles that you decided it to be. And then the next space would be x2, and again, they're all delta x apart. And we don't know what's going on in the middle because I didn't really pick a value, so let's just put like a dot, dot, dot. We don't know what's going on in here. This graph could go on forever. We go up to about right here, and this one's called x sub n minus 1. It's the second to last one, and then b we can write as x sub n. That is how they are labeled. So x naught up through x sub n, they are equally spaced by delta x. That is going to be the width of your rectangle. So when you learned integration, this delta x was the width of the rectangle. And oftentimes we're given a certain number of rectangles and we're going to make an approximation. Now you know how to calculate many definite integrals, so why do we have to now approximate if we can just use our antiderivative rules and just find the integrals? Well, the fact is a lot of functions just cannot be integrated. They don't have an antiderivative. Of course, we don't really see that very often in Calc 1 and not even at Calc 2 at this stage. So in a couple weeks, you will start seeing integrals that do not have an antiderivative, and you will not be able to calculate the the antiderivative, because you wouldn't be able to calculate the area under that curve. Like, you just won't be able to do it. So then you're going to have to go to what we call numerical methods, which this is an example of, which the book titles Approximate Integration. So we talked about the right endpoint, R sub n, that was using right hand endpoints. And again, when we talk about R sub n, this is just going to be a value that approximates the area under that curve, f of x, from A to B, using right endpoints for the height of the triangle. So this is going to be the sum of areas. So I think I just said triangles. I do that a lot. Okay. Sum of areas of rectangles. And remember, what the area of a rectangle we know is the length times the width. So when we talk about the right endpoint, the length in this case, we're going to use the right endpoint to determine height of that rectangle. And that height is just the function at that value. That's going to be, by the way, when we say the length of that rectangle, that is this f at. Now, I'll talk about that x sub I star at the very end of the video. For now, we're just going to use it as f at some value. Where width, by the way, the width of those rectangles are all delta x. And so when we do the right endpoint rule and we want to add them up, we start with, all right, well, now I'm going to erase this delta x. So we know that the width is delta x. So you're going to use the right endpoints. So let's start in the first interval. So the first interval is between x naught and x1. If we use the right endpoint, that means we use x1. We go up to x1 on the graph and we stop. That is going to be the height of our rectangle for our very first value. That value is f at x1. That's this height. This y value is f at x1. And remember, this is delta x. So this rectangle almost looks like a great fit, but it's probably not. That rectangle is going to be, the area of it is going to be f at x1 times delta x. That's rectangle 1. Then we're going to repeat it. We're going to go to the second interval between x1 and x2, and once again we're going to use x2. So we're going to go use the right endpoint, go all the way up to the graph, and that value is actually whatever it is, f at x2. So the height is f at x2. In this case, it's going to be an overestimate in this example. And that area of that rectangle is plus f at x2 times delta x. And we would continue this process until we got to the last interval. And the last interval in this case just happens to be here between x sub n minus 1 and x sub n, or b. And the right endpoint is b in this case. So we go up to the function. The height of that rectangle is going to be f at xn, or f at b, same thing. Then we go over and we graph it. You can see it's an overestimate for this example, not always true. So then we have, this goes on forever. You can see it just repeats itself all the way up to f at xn delta x. And we add this up no matter how many, depending on what our n value is. And that is the right endpoints. Now, if we did the left endpoints, the only thing that changes, if we did the left, it's still left, or length times width, but for the actual rectangles, we don't use the right endpoint, we use the left one. So if I went through, let's see what kind of mess I can make here. I'm going to have to put that curve back on. Let's see what mess I've got here. Okay, how am I doing? There we go. All right, now if we use the left endpoints, that means for the first interval, which is between A and B, A is going to be, f of A is our height, which is f at, we'll say x naught. That's the height. So down here for the left, you're going to have f at x naught times its width, which is delta x. And so that rectangle, again, looks kind of perfect, but don't assume that it is. And then the next rectangle, you go and you find width, and you go to the left one and you go up and over. And the area of that rectangle is its height, which is f at x1 times delta x. And we continue this process all the way up to that last interval, just like we did the last time. We went up to this last interval. But in this one, we're going to use fx at sub n minus 1 as the height. So this one here looks like it's an underestimate in this case, which isn't going to be true in all cases. But we keep going all the way up to f at x sub n minus 1. So we don't go all the way up to n. So those are the left hand and right hand endpoint rules that you learned in Calc 1. And you can see these are sums. So you should have learned that the summation symbol, which is this symbol here, is just adding up pieces all the way up to n. Now, there's another rule that you learned about, which was the midpoint rule, and I do believe that Dr. Lee will go through that, but it's really the same idea, except that instead of just choosing the left, or we'll call it m sub n, sorry, but instead of choosing the left or the right endpoints, you actually just choose the middle of the interval. So I did include a worksheet because I know this gets messy, but you pick the middle. So here you pick this middle and you go up, and that is the height of this rectangle. So you just use the middle of each interval. And you know, there's a couple of different ways. Sometimes if you read some books, they'll call it f sub x1, meaning the first interval, and then they'll put a bar over it, meaning the middle of x1. So sometimes you'll see that, and then obviously you'll go all the way up and keep on doing it. And again, the bar means the middle, and you just keep on going until you do all of your intervals. All right, so even this one here at the end has a middle. So I'll just leave it at that. But it turns out that if you let n get really big, in other words, you know, if you use 4 rectangles, your estimate's going to be poor. If you use 20 rectangles, your estimate's going to be better. And if you used 400 rectangles, your estimate's going to be even better. So as long as n gets huge, what happens is we can then write this summation. Instead of picking an actual value for the height of the rectangle, we just say let it be f at x sub I, so some value in that interval. And like if you go up here and you look at this first rectangle, pick any x value in that interval. It doesn't matter which one. If n is big enough, those rectangles, this delta x is going to be so thin, it's not going to matter what value of x you pick, and then evaluate your function out to get the height. And so we use this notation to represent it doesn't matter what number it is, it just needs to be in that delta x on the x's. And that is where that notation comes from in the formula that you learned in calculus. And the idea is that we want to add them all up, and there's going to be n of them. So this is just another way of writing the sum of length times width plus length times width plus length times width n times. And then, of course, to get the best approximation possible, we then will take the limit as n goes to infinity. And this was the formal definition of a definite integral, which we will come back to in chapter 6 and study some applications. So now what you should do is go watch Dr. Lee's videos. He'll remind you again about the left-hand, right-hand point rules, I think midpoint even, and then you'll learn 2 new rules to use for approximation. And don't forget, when will you need those? Well, one, it's going to be often impossible to find an antiderivative, so that is case number 1. Even though we haven't seen it that often, it's true. And then the other way that, or the other reason you would use approximate integration is when f is found through experimental data. So you don't have a beautiful formula, you just have experimental data plotted, and that is where it is also useful.